So this is the topic for today. EMI debugging with oscilloscopes, part 2. We will talk today about radiated emissions. Last day, in the first webinar, we were talking about conducted emissions. Okay, so we start. Let's go. Well, thank you for attending the webinar. And thank you to MPS and Radiated again for inviting me to participate in this interesting workshop. So let's talk about radiated emissions and how we can make debugging with oscilloscopes. Let's start with the general ideas about radiated emissions. What you do when trying to pass a radiated emission test is to prepare some kind of setup similar to what you see in the screen. Basically, your device under test will be in some specific position, usually on top of a table at some specific height. The table will be non-conductive and the table can rotate 360 degrees. Basically, at some distance, usually this distance is typically 3 meters or 10 meters. In some applications like automotive automation, we use less than 2 meters. No, this can create some kind of problems when measuring radiated emissions, but let's talk about this later. Well, if you put at 10 meters the antenna, remember that usually when measuring radiated emissions, the antenna looks like this. It's an antenna that we build with rods. Basically, antennas with rods are used to measure electric field, not magnetic field. When we measure magnetic field, usually we use loops. So when you are working with the biconical or with the log periodic antenna, remember you are trying to measure electric field. And this electric field that usually we can represent in dB microvolts per meter or something like that, electric field units, is converted to microvolts or dB microvolts, that is voltage, in the output of the antenna. And then the signal goes to the receiver instrument. This conversion can be calibrated, can be measured, and create what we call the transducer factor of the antenna or the antenna factor. Why we don't measure a magnetic field? Basically, the idea is that when we are in the far field, electric and magnetic fields are orthogonal. That means that the ratio between the two fields is equal to a constant, 377 ohms. Why 377 ohms? Because the wave impedance, the ratio between the electric and the magnetic field in the far field, is the result of this calculation. This is the permittivity and the permeability of the media where the signal is being propagated. So the wave impedance is not related with the circuit that was creating the signal. It's the same if the circuit was a high impedance circuit or a low impedance circuit. It's the same. The idea is that the ratio is controlled by the media. And that is because measuring electric field, we can calculate the magnetic field. And this is when we are in the far field. So when you will receive in the far field some specific frequency or some specific signal that is important, that is because in your device under test, you have a good antenna to radiate the signal to the far field. The distance between the near and the far field is something that is not easy to calculate. It's dependent of things like, for example, the size of the device under test. But if you want to do some kind of calculation, you can consider that is something like lambda over 6, lambda over 2 pi, you know? So what you can do when debugging EMI problems is to go close to the circuit. It's like you are Sherlock Holmes, and you can try to analyze the circuit in some way that give you clues to apply fixes. You can use different probes. You can see the signals in the time or the frequency domain, and you can make changes in your design to minimize the signal you are detecting in the far field. Remember, what you are detecting in the near field perhaps is not in the far field, because to be in the far field, you need a good antenna. So signals detected in the near field perhaps will be in the far field, not always. But signals you are detecting in the far field will be found when you are analyzing the near field. And this is what we will try to do, is to understand how the circuit is radiating the signals and how we can go with different probes to analyze the circuit in the near field. So in our product, consider that we are failing in this way. No, you can see a vertical scale and horizontal scale. In the horizontal scale, what we find typically is frequency, and the frequency starts in some value, like for example 30 megahertz, and we can stop here in 1 gigahertz. Sometimes we go to higher frequencies like 6 gigahertz or perhaps 18 gigahertz, depending on your application, military, automotive, or if your product is including some kind of radio frequency device, blah, blah, blah. You will see some kind of limits, commercial limits for industrial, depending on the area of the world where you will be. And then you will see some kind of emissions. If you identify emissions like this one, let me take another color, something like this or this or this, narrowband emissions. Usually these narrowband emissions are coming from some switching circuit, for example, digital electronics or power electronics. No, but the problem we will be analyzing today is when we obtain something like this mountain. No, you can see here that at some specific frequency range, close to FM radio, this is 100 megahertz, is exactly here, we are over the limits some decibels. Remember from my previous seminar, the day number 1, we were talking about trying to go with the emissions below the limits at least 6 decibels, no, to have some kind of a margin. No, if you are close to the limit or you are 1 dB below the limit, this can be dangerous. So who is creating this signal? We talked about this in the first webinar, but basically we have 3 different possibilities. The first possibility is that they are signals in your design. For example, clocks, driving signals, oscillators, harmonics of your oscillators, blah, blah, blah. The second possibility is to have some kind of resonance. The most typical resonant effect we have in electronics is what we call ringing. You have inductance, you have capacitance from the parasitic components, for the parasitic in the packages of the components, from the parasitics in the layout, in the transformers, in general, in the way you are building your circuit. And finally, the next possibility, the last possibility, is to create a parasitic oscillator. No? When you put in your system the input and the output one close to the other, you have gain and you are creating an oscillator that is unintended. So this is what we will be trying to solve today. And to make this analysis, I will be using an RDO6 oscilloscope. The main advantages of the oscilloscope versus other instruments is that for debugging, the oscilloscope will give you the time and the frequency domain of your signal. And additionally, if you have several channels, here I have 4 channels, we will be able to combine different probes to analyze the system and to be able to see if we can apply some fixes. The bandwidth of the oscilloscope usually must be for radiated emissions, at least at the maximum frequency you want to measure. I don't know, 1 gigahertz, 6 gigahertz, something like that. And you need to have a good FFT. With a good FFT, you don't need the spectrum analyzer for debugging, and you will be able to work very easily like you will see in the demos. So let's go to the first part of the presentation, where we will be describing the product. In my product, I have some electronics that is inside of this metallic box. In theory, the metallic box is a good system for shielding. No? Inside of the box, I have an electronics that is being powered by this cable. You can see that I have a red and a black wire, and they are one close to the other, very close one to the other. And if you see with the camera, the power is coming from this voltage here. This is something like 12-20 volts. Is the same system that I was doing debugging in the first webinar. And you can see here the RTO6 in front of the device under test. Obviously, I need to work in a small area, so you can see with the camera. And in a real application, you will work in your laboratory in a better way, okay? So let's consider that we are interested in measuring radiated emissions. The first thing we need is one antenna. So let's go again to the slides. And when you are trying to make debugging with one antenna, you will go to something like this. Remember that you will have an antenna with rods, and the longer rods in this antenna, this area here, the longer rods will be used to measure the lower frequencies, higher lambda wavelength. And the smaller, the shorter rods will be used for measuring the high frequency, in this case, 6 gigahertz. So with one antenna, you will be able to measure from 30 megahertz to 6 gigahertz without changing the antenna. The antenna in this picture is in vertical polarization. That means will be sensitive to electric field that is vertical considering the reference of the floor. No? If we want to measure the horizontal polarization, what we do is to put the antenna in horizontal polarization, no? Something like this. And this is typical when we are measuring in radiated emissions, because in the external lab, in the official lab, what you are trying to measure is the worst condition in emissions, no? And the antenna must be in vertical or horizontal, trying to identify if the emission is coming horizontal or vertical. If we go to the previous slide, in this slide, for example, I have the antenna in vertical polarization. So this antenna will be very sensitive to electric fields that are going in vertical, no? So this electric field is being propagated through the space, is being attenuated, but when the electric field goes to the antenna, create a current in the rod, and this current is what we are measuring in our receiver. But if the electric field is horizontal, because the antenna is in vertical orientation, we will not be able to create this inducted current, and the measurement will be theoretically zero, okay? Usually this measurement is done in a clean area, in a sealed area, in a chamber, or in an open area test site, trying to minimize the possibility to have external noise from the environment or reflections in walls or in metallic structures that are close to the setup. So here is my setup here. Let me try to switch on the light, so perhaps it's better. Now it's starting to be late here in Spain. So you see here the setup, and now we will start with the antenna. For my demo, I will be using this antenna. It's a small antenna. You can see that I have rods. Obviously, it's very, very short. No, it's very nice for traveling or for demos. If I reduce the length of the antenna, I am able to tune the antenna for higher frequencies. If you increase the length of the arms of the antenna, you will be able to measure lower frequencies. Obviously, to have a good antenna for very low frequencies, the size of the antenna will be very big. If I put the antenna in this position, I am measuring horizontal electric fields. If I put the antenna in this position, I am measuring electric field that is vertical, no? In my demo, I will not be very scientific. I will put the antenna in this position, and we will connect the output of the antenna to channel number 1, okay? So this is what we have, basically, okay? So now we are able to switch on the device. But before switching on the device, my recommendation, let me show you the screen of the oscilloscope. This is what we see here, is the output of the antenna. So the antenna is measuring electric field from the environment, and is converting this electric field in a voltage that is going to the channel number 1 of the oscilloscope that you can see in yellow color. This is in the oscilloscope in yellow color, time domain in the horizontal axis. So something that is interesting to do is to see the spectrum of this signal before switching on my device. So I go to the menu of the oscilloscope, and I can go to the FFT. In the FFT, in the top menu, I can start at some frequency, for example, 80 megahertz. Let me start in 80 megahertz. Remember, we know that our emissions are in 120, 130 megahertz, more or less, from the previous slide. And let me stop in 500 megahertz or 300 megahertz, for example. Remember that if you increase a lot the bandwidth, the area you want to analyze, the sweeping of your instrument or the time for make calculations will be longer, no? So I'm going to measure from 80 megahertz to 300 megahertz, and we will use a resolution bandwidth that is, for example, let me use 1 megahertz, okay? And we go to channel number 1. You see how useful is the oscilloscope to see the FFT. The top trace is the time domain, the bottom trace is the frequency domain from 80 megahertz to 300 megahertz. Obviously, I can reduce the volts per division in the top signal, but try to avoid the signal going out of the screen. If not, the FFT will be destroyed. The FFT calculation will be not destroyed. It will be something like if the signal is saturated. So the results will not be good. You can see that I have a lot of signals in the environment. Obviously, if I am not working in a sealed chamber, I have noise in the environment. But if I want to identify signals that are smaller in this area, you see that some signal appears now and then disappear. No, this is something that is in the environment. Okay, so let me go to the FFT menu and see what happens if I reduce the resolution bandwidth from 1 megahertz to, for example, 10 kilohertz. You are going to see two important things. The first thing you will identify is that the noise floor is reduced. So we will be able to measure easier signals that are small, that are below this crazy area. No? The second important thing is that reducing the resolution bandwidth, you will be able to have more frequency resolution. No? You will be able to identify what energy is inside below some specific mountain. So for example, if you see this area here on the left, you see that below this area I have energy, but it's very difficult to see at what specific frequencies really I have energy. No? So going to 10 kilohertz, that is what I am going to introduce now, 10 kilohertz, then you can see that the noise floor is reduced and I am able to identify more signals, okay? Obviously, I am starting in 80 megahertz because I wanted you to see this area here. 80 to 108 megahertz is the area where I am measuring FM radio stations, no? And obviously, in the higher frequency range, I have other emissions from the environment in my laboratory, okay? So this is the ambient noise. Let me switch on my device. When I switch on my device, this is what I get. Look at this. The time domain signal is going out of the screen. So it's very important for a good FFT to reduce the amplitude of the signal so you can see easily in the screen. So now the device under test is on. Let me switch off. We switch off. Now I switch on. So clearly, what I am creating is this big mountain that is over the 108 megahertz of the FM band. This is the area where we are failing, okay? So this mountain you see here is a broadband emission in this area, and obviously I have more emissions here, but consider, for example, that this frequency between 130 and 150 megahertz is the area where you are over the limits and you want to reduce these emissions. So if we go to the camera, the idea is that this energy is coming from my system and is going to the antenna. So one of the, obviously in your laboratory, the distance between the antenna and the device under test will be 3 meters or something like that. And additionally, the antenna will be bigger in size, okay? So the first consideration you have is who is radiating this signal? You have several possibilities. One is the electronics inside of the product. Second is the slots or apertures you have in your enclosure is metallic. Obviously, if the enclosure is plastic, you will have a lot of emissions. And finally, we have the cable. And to understand what happened here, I am going to consider, and not always this is clear, perhaps you need to do some experiments to identify your possibilities. What I am going to consider is that the electronics inside is shielded. So the electronics inside is not being coupled to the antenna easily, but perhaps the energy is going out through the slots or the apertures. But then you need to compare the frequencies you are experimenting the problem with the size of the slots. In my case, if we consider that we are in around 100, 200 megahertz, the wavelength for 100, 200 megahertz is perhaps something like 3 meters. No, if you consider 3 meters, 1.5 meters, you will discover that the slots I have in my enclosure are very small. So it's not easy for these slots or for these apertures to be able to radiate with efficiency a 100, 200 megahertz signal. So in this frequency range, usually the problems are coming from cables. Not always, and especially if the antenna is very close to the device under test, like in automotive application. If you put at 1 meter the antenna from the device under test, you can pick up from the from a small area of your product, for example, from a display or from a small PCB, you can pick up a signal that theoretically you will not be able to radiate to the far field. Anyway, in my product, I know, or I am going to consider that the most important element radiating is this cable. Look at this, the cable is horizontal and it's not vertical. If the cable is vertical, we'll be radiating vertical electric fields. If the cable is horizontal, we'll be radiating horizontal electric fields. So now that I know, or I consider that the noise is being radiated by the cable, I have two possibilities. Is differential mode or is common mode current? Usually in cables, the origin is common mode. Why? Because usually you put the red and the black wire one close to the other. So the current that is going through the red wire and is creating a magnetic field here is canceled by the current that is going in the black wire in the opposite direction, creating a magnetic field that is opposite in the antenna. So in theory, the magnetic field or the electric fields that are created by this cable are canceled at some distance. This is what we call the cancellation effect, and this is what we try to do when designing a circuit we consider to avoid loops. No? So the idea is that I am injecting some kind of common mode current. This common mode current to fail at 3 meters or these typical distances must be not very big. You inject more than 10, 15 microamps of current in this cable, you can fail at 3 meters. So one of the things you will be able to do is to measure the current in the cable in common mode. And this is because we usually work with current probes. So this is the current probe I will be using in my experiment. This one, okay? It's a current probe with a bandwidth of 50 hertz to 200, 400 megahertz, depending on the model. And from the manufacturer, you will be able to have how is the transducer factor of this device, because you are measuring current, but you are obtaining in the output a voltage. And this conversion is frequency related, no? So if we switch again to the setup, what I do is to open, this is very important for a current probe, is the possibility to open it. And I put the current probe in the cable, no? Obviously, something that must be done in real applications is to fix in place the cable. Typically with this kind of tape is very useful. And additionally, remember to avoid movements of the current probe in the cable once you are measuring one time, no? If the cable is long and the frequency is high, usually in some specific position of the cable, you can identify that you have nulls, and some specific position you have maximums. You have a standing wave in the cable, no? So it's important to identify the position that is good for you and to avoid movements. I'm going to put the probe here. Why? Because in my next experiment, I will try to put a ferrite here. If I put the current probe here and save the result, and then to introduce the ferrite, I move the current probe, perhaps the result of the new measurement is due to the ferrite and the new position of the current probe. So let's put the current probe here, and let's connect the current probe in channel number 2. Let me take the cable, coax cable, and connect the cable to channel number 2. This is not very very nice, but I hope you understand the general idea. Okay, let me show you the screen of the oscilloscope. Okay, here on instrument transition. Okay, so what you see here is the previous measurement, is the antenna measurement. So let me activate channel number 2. It's in green color, and we put here channel number 2. This is the activity we have in the cable. It's very similar to the activity I am detecting in the antenna. And now I can plot the FFT. So I go to the FFT. We start in 80 megahertz, same frequency range, to 300 megahertz with a resolution bandwidth of 10 kilohertz for the green trace. And we put here the FFT. Let me put the intensity of the signal higher so all the people can see easily. So you see that obviously the waveform, the shape of the mountain is not exactly equal, because the frequency response of the antenna, of the probe, blah, 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 is different. But you can see that if you have a strong energy at some specific frequencies in the antenna, and the cable is the origin of this emission, you will see a mountain around this area. Okay, so this is electric field, this is current. So if you want to reduce 20 dBs this electric field, what you can do is to try to reduce 20 dBs this current. Okay, so a typical solution for this is to introduce a ferrite. Okay, what I am going to do is to introduce a ferrite in series. So let's go here to introduce this ferrite. Oh no, sorry, it's not here. Let me go here. Here, okay. So this is the ferrite I will be using, this one, okay. So you go to a ferrite, and then you try to find a ferrite that in the frequency range of your interest, 100 to 100 megahertz, I have some specific impedance. If you find that the impedance is basically in the area where the impedance is maximum, this area is typically related with a resistive effect for the ferrite. That means you will be introducing resistive effect, 800, 700, 600 ohms, and the noise will be dissipated. The noise is like disappear, no? If you go to the lower part of the response of the, I'm not sure in this ferrite how is this, but this is the typical resistive effect, and the inductive effect can take a response something like this, no? So the ferrite is offering inductive and resistive effect, and the total impedance is something like this. This is the total impedance that is created by a resistive and a reactive effect. What we are looking for when using a ferrite is the resistive effect. And as you can see in this data sheet, I am interested in two terms, no? So if we go to the camera again, here, okay, here, what I am going to do, perhaps the top view is better to see this. Okay, this top view. Okay, so let's take the ferrite. Before that, let me show you in the camera, in the screen of the oscilloscope, using the reference, I can create, or I can save the result of the injected current in the cable, update here. And we see in white color is our actual measurement to have a reference. And now let me introduce, let me see why. Oh, wow. The mouse is going slow. Now. Okay, so let me introduce the ferrite. Let me see. Here, it's important to try not to move the current probe, okay? So we put two turns like this. Something like this. Sorry. Something like this. Oops. And let me show you how is the current probe, no? So, oops, sorry. Oh, okay, now here. Okay. You can see that with 2 turns in the ferrite, I am introducing here, I don't remember exactly from the data sheet, 800 ohms, and the 800 ohms try to limit the common mode current that is going in this direction. It's important not to move the current probe. So the current probe must be exactly in the same position where you measure the reference signal. No? If we switch to the screen of the oscilloscope again, you can see the difference. So here, if you consider that I have 10 dBs per division, I can consider that in this frequency range of around 110, 120, 130 megahertz, I am reducing 15, 20, 10, 15 dBs emissions. This is a typical result from a ferrite. A ferrite is not usually able to reduce 40, 50 dBs your emissions. No? And additionally, the effect of the ferrite is relative to the terminal impedances that usually are unknown, okay? So you can start to consider to filter or to seal the problems, no? Another important tool for debugging is the near-field probe. Let me show you the near-field probe. Okay, so we go here, and near-field probes can be electric near-field probes or magnetic near-field probes. Electric near-field probes are useful for measuring electric fields, and they are very useful when you are interested in DVDT. Magnetic near-field probes are loops, and they are very useful when you are trying to identify where you have DIVT, magnetic fields. No, they can be big loops or small loops, big tips or small tips. The idea is that if the loop or if the tip is big, you will have more sensibility and lower bandwidth. But sorry, if the probe is big, you have less bandwidth and you will be more sensitive, but you will not be good in a spatial resolution. If you reduce the size of the loop or the size of the tip, you will have the possibility to identify exactly at the pin level or the trace level where is the origin of the signal, and with a higher bandwidth. Okay, but the probe will be less sensitive. So this is what we will try to do now. Let me show you the screen of the oscilloscope and now the picture. No, so if we try to do this with a near-field probe, let me take this near-field probe here. It's a medium-sized loop. Okay, that I will be connected to channel number 3. Okay, so let's go to the screen of the oscilloscope here. Oops. And let me activate channel number 3. Channel number 3 is in orange color. We can put channel number 3 here. Look at this. I am using 3 channels at the same time in time domain and in frequency domain. Let me plot the FFT from 80 megahertz to 300 megahertz with a resolution bandwidth of 10 kilohertz. Oh, sorry, 10 kilohertz at the orange color. And then we put the FFT in the lower part of the screen, okay? So you can see that I have yellow color is the antenna, time frequency domain, green color is the current probe, time frequency domain, and orange color is the result of the near-field probe. If we try to see how is the measurement with the probe, we can go here and we can go around the system. No, if I go close to the cable, this is what I am going to do. Okay, if I go close to the cable, I will identify the peak. This is what I am going to do in the next view of the oscilloscope screen. No, let me switch to the oscilloscope screen and look at the orange color. I am far from the cable. I am close to the cable. So I am able to identify where I have energy. I can test around what cables I have a specific activity. Or, for example, I can go around the slots. No, I am going to do this in the next view of the oscilloscope screen. Okay, so here you can see, look at the orange color. You can see that the energy is going out of the slots. This is dangerous for emissions? No, because these slots are not able to radiate to the far field. But if you see here I put a small cable that is inside of the PCB close to the slots. So the energy is in this area, and the energy is able to be coupled to external cables, no? So for example, you have some kind of external cable that is close to the system in this position. The energy can be coupled to the cable, and the cable can be a good antenna to re-radiate the signal. No? So what is inside of this product? Usually, what we try is to solve the problem at the circuit level, no? It's exactly the same circuit I was working with in my first webinar. So let me show you here, and you see, let me show you the PCB. I have a PCB that is powered with this cable, this 20 volts, more or less, and the output 12 volts is powering this fan. And this cable, the load cable of the DC-DC converter, is the cable that is going close to the slots in the cover of the enclosure, okay? And the energy that is here is being coupled to the slots, no? So where is the origin of the signals I am radiating inside of the DC-DC converter? What I can do is to change to a smaller loop, something like this, and then I can go around the circuit. I am going to do this in the next view of the oscilloscope screen, and especially I will finish around the inductor in the DC-DC converter, no? So we go to the screen of the oscilloscope, and let's go around the PCB, and this is what I see when I get very close to the inductor in the DC-DC converter. So you can identify exactly where you have more energy. So something that you will do probably is to try to identify who is creating this energy. Remember, this is not harmonics of your signal. I am not switching at 100 megahertz. They are not harmonics of my 500 kilohertz switching frequency in the DC-DC converter. Perhaps it's an oscillation, perhaps it's a ringing or resonance, no? So let's go to the screen with the camera, and let me use this similar PCB. It's exactly the same PCB, and I am going to unpower the other one. Let me go here to introduce the power to this device, and let me take the fan outside of the box to connect here. Okay, so now the system is working. Let me show you the screen of the oscilloscope. You see that this basically is very similar. It's not exactly the same because the two PCBs, they are not exactly equal, but you can see that they have the mountains in the same frequencies. And let me see what happened when I go close to this area. I see the energy. So something that I will do is to check how the circuit is switching. So to see how the circuit is switching, I will do the preset of the oscilloscope, and I will connect to channel number 1, a passive probe, okay? Something like this, okay? And obviously, to see how the circuit is switching, I cannot use the pigtail of the probe, okay? So I am going to connect in this way, okay? So I have prepared my PCB. That is because I have changed the PC board. I have introduced it here, the pin to the drain that is switching. And here I have the connection to ground, okay? So let me show you the screen of my oscilloscope. But first, consider that my oscilloscope could be, for example, a 20 megahertz oscilloscope. What happens if your oscilloscope is a 20 megahertz oscilloscope? Okay, this is the signal of the switching activity. You see this, okay? We switch in this way, and we adjust the trigger. So this is a typical switching signal in a DC-DC converter, okay? So my oscilloscope is now with a bandwidth of 20 megahertz. What happens if instead of limiting to 20 megahertz the bandwidth of the oscilloscope, I increase to full bandwidth? My oscilloscope is 2 gigahertz in bandwidth. Not necessary for this application 2 gigahertz, but this is what I am going to do. I open the menu, and in the bandwidth, go here to activate full waste bandwidth. From 20 megahertz, let me put full. And this is the difference of a high bandwidth instrument or a low bandwidth instrument. Okay. Obviously, if we open the switching activity. Here is the difference. Here is the difference. This frequency, this ringing, is what is creating the anomalous emissions. So how can I remove this ringing? You have different possibilities. This is very related with the layout of the PCB. Francesc Estragués was explaining in the first presentation how to do a good layout for minimizing this kind of effects. Or perhaps in some specific application, you can try to kill the ringing. Usually the ringings can be killed with snubbers, with resistors, or with ferrites, depending on your application. No? So this is what I'm going to do in my demo. Again, if we go to the screen with the camera, let me disconnect again the new PC board I was using. Let me work again inside of the box this way, and let me power again here externally this way. Okay, now I have again the same product like before. Okay? Let me remove the board where I was measuring the ringing. Perhaps we can try to identify how is the ringing here. Now, let me go here to remove the ferrite. So we create a very anomalous situation. And let me close the product. Okay. And now we will repeat the measurement. No? Now, let me go to the screen of the oscilloscope. Let me see what happened with the antenna. Connecting the antenna to channel number 1. Okay. What I see in channel number 1, let me activate FFT from 80 megahertz, 80 megahertz, 80 megahertz to 300 megahertz. Oh, sorry. To 300 megahertz. Stop frequency 300 megahertz and resolution bandwidth 10 kilohertz. Okay, this is my first measurement. No, this is the antenna. Let me activate channel number 2 to see the output from the current probe in the cable, measuring common mode current. Activate FFT from 80 megahertz to 300 megahertz. Okay, with a resolution bandwidth of 10 kilohertz in channel number 2. It's the same like before. Okay, so I have the mountain. No, let me open the box. I'm going to open the box. And what I am going to do now is to go inside of the PCB, and I'm going to remove this jumper. What is this jumper? Later we can talk about this, but this jumper is trying to introduce a small Ferrite bit in the switching activity of my DC-DC converter. So if we go to the screen of the oscilloscope, we go to reference, and we activate for math number 2, the reference 1 here. Let me put here in the middle like a reference. And let's go to the screen to remove this jumper. Okay, and this is the result. You see, I have removed it completely, the emissions, the broadband emissions, because the ferrite is killing. This is not a magical solution. You have another risk with the ferrite bit, but this is to demonstrate that with something that in theory is very cheap, is introducing a small ferrite bit. But the jumper can go in and out to short circuit the ferrite. This jumper is short circuiting the ferrite. So it's very, very nice to see how, if I introduce again the jumper to short circuit the ferrite, so the ferrite is not working, you can see the jumper is now on top of the 2 pins. Now, if I introduce the jumper more and more, the parasitic inductance that is around this ferrite is changing. So now look at where is the peak in the green color trace is. And when I am introducing, you see that the peak is going to the right. This is because the inductive effect of the jumper is very important. They are, I don't know, 5, 6, 10 nanohenries. But with these 5, 6, 10 nanohenries, I have the possibility to do some kind of tuning of the LC parasitic effect. And finally, let me disconnect this and see what happens if I use a good layout. What I am going to use is the same PC board. I will not describe the design techniques today, because it's in the first day webinar, and I hope you have the recording. Okay, this is the board that I was using from MPS. This is a board with 4 layers and trying to work with a specific good layout. Many of the techniques included here were explained by Francesc a few hours ago, not 2 hours ago. So let me power the board and let me see how are the emissions, okay? For the people that was not attending the first webinar, this is a DC-DC converter, okay? It's a buck converter down, that is powered in the same voltage. I am going to power it with 20 volts, okay? And I have here a resistive load to make the circuit switching at maximum load. Let me switch off the lights and let me switch on the lights in the camera, so perhaps it's better, okay? And now, let me show you how are the emissions when I switch on the device. Let me go to the screen of my oscilloscope here. Let me remove the reference 1 because it was from the previous experiment. And let me remove the green color that is the result of the current probe that I am not using now. No? So now what you see here is basically the antenna. The device under test is off. Remember, the device under test is this. Let me go. I am close to finish, okay? So here I have 20 volts. This is the DC-DC converter. I have 3 volts here that are powering this power resistor, okay? So because the device under test is off, this is the result of emissions. Let me save in memory, update. Okay, so let me see, math 1, update. So this is my reference of my emissions. Let me see what happened when I switch on my device. Really, you need to believe me. Now the switch is, the device is on. You see? There is no difference. No emissions. The product is not inside the box. The product is using a big cable, but all the noise is contained inside of the 2 layers of the PC board. And if you don't believe that the DC-DC converter is working, what we can do is to go to the full view of the camera here. And I am going to use the NIFI probe, okay, again, connected to channel number 3. So we can activate channel number 3. We see here channel number 3 in orange color. Let me show you the screen of the oscilloscope, okay? This is the time domain, top left, time domain, bottom left, frequency domain of the antenna. Bottom right is the FFT of the antenna that was saved in memory. And top right is the output of the NIFI probe. And you can see that when I go close to the inductor in the DC-DC converter, you can see that I have the noise that is created by the DC-DC converter. So the DC-DC converter is working, but emissions are very, very low, almost difficult to measure in this application. So I hope you enjoy this. It really is difficult to work with all these topics in only 40 minutes. Anyway, I hope you enjoyed the presentation, and I will be happy to answer any questions you have about this presentation or any topic in EMI EMC.
Thank you very much, Arturo. I see we already have a couple questions in there, but just to let everyone know, if you mouse over your Zoom webinar interface, you'll see a Q&A button, and you can type questions in there. And once again, a reminder that all these sessions are recorded. They will be available on demand within the next couple of days, and we will be sending you an email about where to find them. All right, the first one was, how do we determine the maximum radiation for orientating the antenna? Conversely, what if the radiation is neither horizontal nor vertical, but rather at an angle relative to the horizon?
Yes, it's a good question because electric field perhaps is not vertical or fully horizontal, but considering that in many official regulations you need to measure in both orientation, that is because I am working with vertical and horizontal. Obviously, if you have a electric field that is not specifically vertical or horizontal in other position of the antenna, you will have higher emissions, no? But regulations are measuring in horizontal and vertical only. So that is because I was doing that.
Next up, what would be some steps that can be taken to hide radiated emissions into a diagonal plane? Is this even something that's possible?
To hide radiated emissions into a diagonal plane. Sorry, but I don't understand the questions. Sorry. I don't understand the question. Sorry.
If you want to try and clarify, we'll try and swing back to this one again.
Yes, of course.
After the next few.
If not, I can answer by email if not possible in time. Okay.
Great. Thanks. Where is the ferrite connected in the circuit? The ferrite reduces the noise.
Good question. Let me switch to the slides. This is the slide. This is the slide I was using in my previous webinar. It's the same DC-DC converter. And you know that the switching node with the high DVDT activity is here. This is a switching node where we have a strong DVDT of the transistor switching. So what happened here? You have inductance. We have inductance here. We have inductance distributed through the layout. The layout of my PC board is not like the layout from MPS with good ground planes. It's a 2-layer board, and I have some kind of nanohenries in this layout, no? And I have parasitic capacitance related with the transistor, to the ground, in the diode, blah, blah, blah. So the position for my ferrite is exactly here. What I am trying to introduce is a ferrite here that can create some problems in the DC-DC converter. But if you select correctly and you check the behavior of the converter, you will not have problems, no? Anyway, my idea was to demonstrate that if you have a ringing, something like an inductance and a capacitance that are ringing, no? If you excite with a square wave signal L and C, and you don't have losses, the output will be doing something like this. This is what we call underdamp situation, no? If you introduce a resistive effect in some position in this LC circuit, what you do is to damp the resonance, no? It's the same idea with snubbers, no? But in the demo, I am introducing the ferrite here, no? So the jumper I was talking about, the jumper is a jumper that is exactly here. This is one pin, this is another pin, and the jumper is here. So when the jumper is in position, it's short-circuiting the ferrite, top to bottom. And when you have seen that the mountain was moving left to right, right to left, when I introduce and move the jumper, the idea is that here in these pins, I have some kind of parasitic inductance, no? So reducing the, introducing more and more and more the jumper in position, the inductive effect for the switching node is reduced, and then the peak of the frequency go up in frequency. If you put the jumper here, the inductive effect for the switching node increase, and because the inductance is higher, the peak of the resonance goes down. That is the idea.
Great, thank you. This one is, why do all the evaluation boards have input and output ports on the opposite sides of the PCB and not both connectors at one side or edge of the PCB?
Well, I suppose that evaluation boards are created to demonstrate the behavior of the integrated circuit. If you are considering EMI, you have two possibilities, no? What I usually like is to put the input and the output in opposite sides, no? This is the idea. This is the input cable, and this is the output cable. With this configuration, you do what? You have the best situation to avoid coupling, between the input and the output. If you put the output connector close to the input, you have more probabilities to have coupling between the input and the output, and for example, to have problems, immunity or emissions, depending on your setup, no? So advantage to put the connectors in opposite sides is to avoid coupling between the input and the output. And probably this is because many evaluation boards are done in this way. But be careful, because in some situations, if you put the input connector here and the output connector here, and this is the cable, what you can be creating, this is dependent of how you do the layout of the PCB, what you are creating here is the possibility to excite of this voltage a dipole, okay? So if you create a dipole, you will have a current that is doing this, yup, 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 from left to right, from right to left, and at the frequencies where this is lambda/4 and this is lambda/4, you are creating something close to a parasitic dipole. If you put this cable in the same area, it's like if you have one antenna, remember the antenna I was using in my demo. To have a good antenna, this arm and this arm must be one separated from the other. If you put the arms one close to the other, this will not radiate, okay? So with connectors, with cables that are one close to the other, you minimize the possibility to have parasitic dipoles. But you have advantages and disadvantages.
Next up, aren't there impacts on the disturbances due to the fan?
The fan can have effect in two parts. The first one is that the cable that is powering the fan is not filtered. And the second one is that the fan is the load of the DC-DC converter and can do the DC-DC converter working in some specific way or another, no? So see, yes, the load of the DC-DC converter can have effect in the emissions from the DC-DC converter.
Okay, what is the reasoning behind having one turn or more turns for ferrite? What defines that?
Yes, if you have a ferrite like this one, and you introduce the wire through the ferrite, this is one turn, you can observe that the impedance you get is something like this, for example. So I don't know, at this frequency, I have 600 ohms. If you take the cable and instead of introducing one time, you make one time through the ferrite and another second turn, the idea is that it's like if you are introducing 2 times the impedance. So what you will be expecting is that the impedance you are offering is higher. But the effect in the real ferrite is that usually you increase the impedance, not to the double value, you increase the impedance, but the peak is decreased. So be careful about this, no? Because if you are working at this frequency, for example, going to 2 turns can be interesting, no? This is 2 turns, this is 1 turn. Can be interesting because you are increasing the impedance in series for the common mode. But if you increase to 2 turns and you have the EMI frequency here, look at this, because you are reducing the peak, perhaps the impedance is decreasing. So you think that you are going to increase impedance, but really you are decreasing the impedance. This is because, like with inductors, you have parasitic capacitance between the turns, and the component is bigger, and these parasitic effects reduce the bandwidth.
Great, thank you. Next one is, where was the tuning jumper located? In parallel with the power supply to the big decoupling cap?
No, it was here. This is what I explained. It probably the question was sent before I was explaining. You know, the jumper is here, is short circuiting a ferrite that is in the output of the DC-DC converter to demonstrate that the ferrite can kill a resonance. No, I insist that be careful about this technique. And additionally, with this ferrite, we are introducing inductive effect. The inductive effect at low frequencies can create increase in emissions, in conducted emissions. No, if you have the converter switching in this way, no, you are the converter switching in this way. Perhaps later you will switch in this way. The frequency is lower because you are introducing more inductance, and you can identify an increase in emissions, in conducted emission below 30 megahertz. Okay.
All right, and I think you've already covered this one. Where was the ferrite placed in the circuit? You've got that right
Okay.
there. Let's see. How do you manage to contain the SN oscillation within the PCB and not be coupled into the VN, GND, or the V out?
Oh, I suppose that this question is related with the MPS evaluation board, no? If you look at the evaluation board information, you will see that they are using 4 layers with a good layout of the ground planes. And additionally, they have a good decoupling capacitors, high frequency capacitors for filtering the activity. And additionally, they have introduced filters in the output cable. So this is the secret of EMI. EMI is the technique to control or to contain electromagnetic energy where you want, avoiding to arrive cables or other elements that can be good antennas. So my recommendation is to check the evaluation board information. I think it's in the you will see in the slides that you will receive, you have the reference, and if you want this one. Okay, this is the evaluation board that I was testing, this one. So you have this information in the web, MPS website.
Thank you. This one is, I have some radiation I discovered from decoupling capacitors with loop antenna. Do you know what that could be?
I have some radiation I discovered from decoupling capacitors with loop antenna. Do you know? Oh, I don't know if with loop antenna he wants to talk about some kind of near field probe or something like that, because from the coupling capacitor is difficult to identify. If you look at one of the pictures, one of the slides of Francesc, he was explaining that you have here the integrated circuit, and this is the V-in node. If you put a capacitor for decoupling, this is my capacitor, SMD capacitor, and this net is connected to ground. So the idea is that the integrated circuit is requesting current, switching currents, no? So if you put a capacitor, the capacitor is extracting the current through from the ground to the through the capacitor to the device under test, and then is returning to the capacitor, no? So you have here a small loop. That is because Francesc was explaining that the technique to reduce the emissions from this capacitor is to put a capacitor that is symmetrical, no? Because then the current goes in opposite direction, and then you have 2 loops. This loop, you have this loop with currents in different directions. So the magnetic field at this point is minimized, no? Because one of the loops cancel the magnetic field created by the other. So I suppose that you are, with a near field probes, identifying that around your decoupling capacitors or capacitors that are in parallel, you have these high frequency currents.
Great, thank you. Let's see. The diagonal plane will have cosine and sine components of the horizontal and vertical antenna fields.
The diagonal plane will have cosine. Yes, correct. This is related with the previous question, perhaps.
I just missed these through here, and I can't see the.
The diagonal plane from this comment is the idea that if your device under test is here and is radiating, here you have the antenna measuring some polarization. So if the electric field is vertical, you can plot electric fields in this way. Magnetic field will be horizontal, okay? And it's going in this direction, okay? So this is the plane. This is the diagonal plane, is where the electric and the magnetic field are contained. And the product of the electric and the magnetic field is what we call the Poynting vector. This is in the far field. So this is the idea, but I don't remember how to apply this to the previous question. Sorry, I forgot it.
Well, let me, I think I he typed in some more, so let me try and read this all together and see if this makes any more sense. Sorry about that. So we start with diagonal plane will have cosine and sine components of the horizontal and vertical antenna fields. Therefore, the emission can't be hidden in the diagonal plane. I think that was the full of it.
Yes, probably is referring that in the diagonal plane you don't have emission because you are receiving the plane wave orthogonal to the diagonal plane is the pointing vector.
Okay, great. And then this one just says in low frequency 1 megahertz, and it's not switching frequency. I'm not sure what they're addressing it. It was while you were still giving the presentation, it looks like, though. So let's just... do you generally recommend an RC snubber between the SW node and the GND?
It's not mandatory. It depends of the layout you have, the size of the package of your components, and if at the end you cannot minimize the nanohenries and the picofarads of the resonances, you will need some kind of snubber to avoid the peaks. So I recommend to minimize the possibility to have ringing with a good layout and components placement. And if this is not possible, pues you will need the RC snubber. RC snubber sometimes is impossible to avoid in flybacks, in the diode, in the output of the flybacks secondary, in the secondary of the flyback, or in other switching activities. So it's not really that I recommend. Is that in some application is mandatory, you know. But with good layout in the PC board I have presented from MPS, I remember that there is no RC snubber and the emissions are minimum.
Okay, thank you. Let's see.
This can be the formula to find how is the field at some distance in the, yes, probably. I don't remember exactly the formula, but probably yes, I suppose.
Well, if you, are you seeing his formula in this one? It's actually coming across 3 different questions, Arturo, if you see it all.
Yeah, this is the formula related with the area, a loop that has with area A, where you have a current I at some frequency, F2, and you want to see, to calculate how is the field at some distance D. So, yes, these kind of formulas are useful to estimate how will be the current, the electric or the magnetic field at some distance, yes.
Great. Some thank yous to you. Let's see. Can you use a circular antenna and receive all the polarities?
But you will not be able to identify if the polarization is vertical or horizontal. This is very useful. If you are able to identify if the orientation is vertical, if the polarization is vertical or horizontal, this is a very good clue to identify if the emissions are coming from horizontal cables, vertical cables, horizontal slots, or vertical slots. So you have another kind of antenna that with the possibility to identify different polarizations, you will see the signal, but you will not be able to make debugging in the same way.
Great, thank you. This is going back to an earlier one, if we can keep them all straight. To clarify the earlier question, if I have good results in the horizontal antenna orientation, but bad results in the vertical orientation for radiated emissions, what would be the steps to move in between?
Okay. Well, this is very difficult to answer, but let me consider that your product is a box like this one, and you have a cable, power, data, or something like that. And like you say here, you are failing in vertical or in polarization, not in horizontal, no? So if this is the table, and considering that you are failing at frequency from 30 megahertz to 400 megahertz, let's say something like this, my impression would be that you are failing because you have cables. I am considering that your device is not something like a big rack, no? I'm considering the size of the product not very, very big, no? So if you have, for example, some kind of horizontal cable to some accessory, this is the horizontal cable, and this is the vertical cable. If you are failing in this frequency range, 30 to 400 megahertz, and you are failing in vertical polarization, in my opinion, the culprit could be the vertical cables, okay? If you increase the frequency, if you go from 300 megahertz to, I don't know, 1 gigahertz or something like that, you need to look for smaller systems. Obviously, the cables can contribute in the same way, but we will look additionally for smaller elements that usually are slots or apertures if your enclosure is metallic, no? So for for vertical polarization, you will look for horizontal slots, and for horizontal polarization, you will look for vertical slots, okay? It's the opposite, no? An horizontal slot create a vertical electric field, and a vertical slot create an horizontal electric field, no? If you work with the near field probes, you will be able to identify what kind of part of your system is the good antenna. This is one important thing, is to identify where is the antenna, so you are able to try to minimize his effect. No? If the case is plastic, probably you can radiate at higher frequencies with the PCB if you don't have a good layout. No? Many possibilities.
Thank you. How can we estimate what frequencies measured by the near field probe will radiate? Calculate the cable and slots dimension with respect to the frequency.
Where is the question? Let me see. Where is the question? See,
Are you seeing it okay?
I don't see the question. How can we estimate, no? What frequency measure?
How can we estimate what frequencies measured by the near field probe will radiate? And then it has a follow-up of calculate the cable and slot dimensions with respect to the frequency.
If you consider that you are in the far field, a typical rule of thumb, but this is a complex idea, is that you no radiation if size is very small compared with lambda. So you take your frequency, and lambda is 300 over the frequency in megahertz, with lambda in meters, no? So a typical rule of thumb to calculate to avoid emissions is that the size must be smaller than lambda over 20. This is what we, in commercial application, we can consider that is small. Lambda over 10, lambda over 20, depending on the system, no? If you go to some specific application, like military or things like that, you can go to lambda over 100. Lambda over 100 is a more safety rule, but the problem is lambda over 100 is usually more difficult to implement or perhaps more expensive, no? Depending of where you apply this rule, in shielding, in cables, or in PCBs. But the idea is to compare the lambda with the frequency where you fail. That is because here, if you see when I was saying that you fail between 30 megahertz is 10 meters, and 400 megahertz, let me write 300 megahertz is 1 meter. So what parts of your product are usually good antennas between 30 megahertz and 300 megahertz? Systems that are not very small compared with 1 meter and 10 meters. That means cables, for example. Okay.
Gotcha. Thank you. Is this essential to have the antenna factor considered during measurements with the oscilloscope?
No. It's a good information, but usually when we are doing debugging, we look for qualitative differences. No, we are not specifically interested in some value of voltage or current or something like that. Obviously, if you want to identify how much is the current that you are injecting in the cable in common mode, you need to have the factor for the current probe, so you can convert volts to current to microamps or something like that. In the antenna is the same. You want to identify how many dB microvolts, but in debugging in your laboratory without a sealed chamber or with some limitations. What you want to see is what happens if you change the software, you add a spread spectrum, and you put a ferrite, or you move some specific part of the system to see if you reduce 3 dBs, 10 dBs, or 40 dBs. No.
Great, thank you. This is are all the oscilloscope measurements done here near field ones?
In my demo, probably yes. Yes, I am not working in the full far field because I am working at, you have seen I am working at 100 megahertz. 100 megahertz means that the lambda is 3 meters. So to be in the far field, I need to be 3 meters divided by 6. No, so I need to be at least 350 centimeters far from the distance, more than 50 centimeters of distance between the antenna and the product. So no, I am not doing a good far field measurement, but this is the way to do this on top of a table, blah, blah, blah.
Great, thank you. And again, I'm not sure about going back to diagonal versus horizontal, but it's this, he says, diagonal plane is not requested by EMI standards.
No, I think no.
Okay. Why does your circuit not have a earth connection, and why capacitors to reduce the EMI?
Well, earth connection is a question related with safety. So if the voltage you are working with is not unsafe, I was working with 20 volts, there is no need for earth connection for user protection for electrocution, no? So I have not Y capacitors in these applications. The Y capacitors are used normally for conducted emissions up to 30 megahertz. What I have not shown in the demo, we don't have time, is the idea that another possibility for filtering is, instead of using a ferrite in series, is to use a free-through capacitor. No? Let me show you here. If I show you the camera, here I have two free-through capacitors. This is something like, it's not the same, something like the idea of a capacitor from line to earth and neutral to earth. No? In this case, from positive to chassis and from negative to chassis. So with some kind of cable, I can power my board from here instead of going through the enclosure. And then I have two capacitors in some picofarads, and they are connected at 660 degrees to the metal enclosure. This is a very, very nice way to filter high frequencies, hundreds of megahertz. No, I did not have time to do this demo, but the effect is very similar to the ferrite effect. So very similar.
Okay, thank you. Is a switching low side MOSFET of a boost converter where there's a shunt resistor to measure overcurrent from source and G&D, where should the RC snubber be connected? From switching node drain to G&D, or between the drain and a source?
In my opinion, it's from the drain to the source, but I cannot answer this question totally sure about that. No.
Okay. Does a regular light bulb generate high EMC?
If with regular light bulbs you mean a resistive effect, like old bulbs, the answer is no. It's like with a resistor. The problem with lights today is when you are working with LEDs, that they are using switching power electronics. No.
Thanks. And then how to reduce radiation from cables if the cable length cannot be reduced?
Oh, good question. But this is not very difficult to answer. I think. Look at this. This is your product, and this is the cable that is radiating. obviously you can, one possibility is if you reduce the length, you will radiate less, or you will need energy in higher frequencies to be able to radiate. So in this application, I cannot reduce the length of the cables. The first things you must consider is that both wires or the end wires of the cable must be very, very close one to the other. In this way, differential mode currents will not be able to radiate. If you do something like this, you take your red wire, and the red wire is separated from the black wire in some millimeters or some millimeter, you will radiate in differential mode. So the first idea is to put one exactly, one close to the other. The second idea, the cable is something that is passive. So if you are radiating, it's because you are exciting with noise. So the second important idea is to kill the source. For example, if this is a ringing, you kill the ringing and you will not be able to excite this cable independently of the energy of the frequency or the length of the cable. And another solution is if you introduce for this signal some kind of filter, no? Ferrites, capacitors, inductors, depending on the application, the frequency, blah, 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 no? So the first, let me write here, the first solution is a small loop. The second solution is kill the source. The third solution is filter. And the fourth solution, perhaps this is the last option, is shielding, no? But shielding with a good technique, no? Sometimes people add shielding in cables, and at the end is the screen of the shielded cable who is radiating. So it's very, very important to do a very good connection of the shield to the chassis, no? So I think that these four solutions are the most important things you can do.
Great. Let's see. If one ferrite clipped on the cable is not enough, can I use 2 or 3?
Yes, you can use 2 or 3 in series, and you will be introducing more and more impedance. But probably the customer will say no. Probably this is not permitted in many applications. But technically it's possible.
Okay, and then I think back to your drawing that you're on there. There was just how do you kill the source?
The key to kill the source is what I was explaining, no? In my demo, one possibility to kill the source is you have a circuit where you have a ringing, and if you look at the signal without the ringing, oh no, in this way. So what happened? You are creating, I don't know, this kind of emissions, this mountain, okay? This is related with this frequency, okay? So if I add a snubber or ferrite like in the demo, I convert my signal in something like this, and then the emissions or the profile of emissions goes down. So why is this kill the source? I am killing the source because the energy that was created and radiated is not necessary in my circuit, and I make it disappear, no? You have another possibilities for, I don't know, for example, you have a circuit and it's not very good decoupled, you can introduce a good decoupling circuit, depending of the application, to minimize the possibility to have high frequency current in the power lines, no? High frequency not permitted in the VCC or the ground lines, no? You can try to work inside of the circuit to avoid this energy. For example, another possibility, if you are working with this kind of signal, switching very fast, perhaps you can try to switch slower, no? This is a technique to minimize, I don't know. It's to minimize the possibility to create emissions. In one of the speaks from the first day seminar, we saw that if you have a signal that is being switched with a fixed frequency, if we apply a spread spectrum, we can remember from the Florian talk, the spread spectrum spread the energy in the spectrum and the peak is reduced, no? This is another technique to kill the source. Like, you are not in this last example killing, but you are reducing the origin of the problem, the energy of the origin of the problem.
Very good, thank you. And just a heads up, we're gonna cut off any extra questions here at the top of the hour. So I thought we were just about to get through, but they keep coming. So here we go. We'll give it another 5 minutes worth. Any advice to reduce bulk current induction for twisted pair, but a 25-meter long truck harnesses? I've got that right.
No, probably the only possibility is to filter, I think. Filtering is what I think. I consider that you cannot shield, no? If not, shielding is another solution.
Can we twist the cables to reduce capacitance?
I'm not sure what capacitance he's explaining, but consider that if you have a red and a black wire, and one is close to the other, very, very close one to the other, and you compare the capacitance between the cables when you make a twisted pair, something like this, the effect of the twisted pair is that capacitance between the wires increase, is not reduced. But this is not bad. Perhaps it's bad or not, depending on your application. No? But twisting, you increase the capacitance between the two wires. Not sure what kind of capacitance you are interested.
Thank you. Can you use a standard AC line filter on the power source input? What about to feed through the caps on the connector?
Yes, if I am understanding that you refer that your product is powered by DC and you want to use an AC line filter, well, the low pass filter response will give you the possibility to apply a DC voltage. This is what I am doing here in my demo. Okay, I am using a filter. Let me show you with the camera. In my demo, my 20 volts goes to the device under test through this filter. This is an AC filter. So DC is going through, and I am filtering any noise from, I don't know, 150 kilohertz to some megahertz that create a quiet power supply for me, no? Obviously, I don't know what application you have. And about feed-through capacitors is what I have been explaining in when I was showing the feed-through capacitors in my box, no? These capacitors that are similar to the Y capacitors, no? From line to chassis, from the other line to chassis.
Thank you. All right, I think this is the last one, and then we'll send emails out on the couple remaining. Why ringing creates a broadband frequency if it oscillates at one frequency?
Oh, this is a very good question. This is the idea. You are switching in this way, and you have here a frequency that is more or less constant, no? Usually it's more or less constant, no? So your first idea is that if the signal has this spectrum, your idea is that because you have this ringing, you will be increasing the energy at a frequency that is in the same value. But why we see something like this? Why we see a mountain instead of a peak at the frequency where you have the this ringing? What you need to consider is what happens if you see a signal that in time domain is doing something like this. This is time domain, no? It's a peak. It is repetitive, no? So what you need to think is the signal is repetitive. Constantly, you have this peak here, no? So it's like you have two signals. One is the square wave signal. The other is the underdamped ringing. But the underdamped ringing is periodic, okay? So if you remember from the school, the Dirac delta has an FFT that has a flat response with some specific amplitude to the infinite, no? So what we have here really is a ringing, a ringing, a ringing, a ringing, and that is because this energy is not at one frequency. It's a repetitive signal with a very sharp response. But this mountain that you are creating is around, the maximum is not around, is not exactly F0, but it's close to F0. That is the idea. It's a pulse that is repetitive.
All right. Thank you very much, Arturo. I think
Okay.
at that point, we're going to have to call it good for the day. For the last couple questions, we'll send you out answers on those ones. But thank you for all your time and all the thorough answers, Arturo. That was a lot of good stuff today. And for everyone that attended and attended last week's as well, we very much appreciate you joining with us and working through a lot of these different scenarios.
Okay, thank you. Have a good day.
Thanks, everyone. Bye.
Bye.